Hello everyone. For this tutorial video, I would like to demonstrate how to prove the circumference of a circle, as well as the area of it, and also explain why pi has the value it has and not any other. If we remember from our lesson on regular polygons, the greater the number of triangles in a polygon, aka the greater the number of sides, the smaller each triangle or side length will be, but also the greater the perimeter. If we take this to its most logical extreme, we can see that we will form a continuously smooth perimeter that does not look like it is made up of straight lines. Surprisingly, however, this infinitely smooth perimeter does not have an infinite perimeter, even though we used an infinite amount of lines to estimate it, but instead approaches a specific limit. This infinitely smooth perimeter is called the circumference, and is equal to 2 pi times the radius. We can prove this is true visually by drawing two circles that overlap in a way very similar to a Venn diagram, so that the edge of the first circle is at the center of the second circle, and vice versa. Next, draw a line connecting the centers of the two circles, which is simply the radius of both circles, owing to how we drew the circles. Next, we draw two lines to the points where the circles intersect, which will give us two triangles. We should also see that the triangles are equilateral, i.e., the length is the same on each side, and so because one of their sides equals the radius from what we drew earlier, all of their sides will equal the radius. We next extend the radius of one of the circles to the full diameter of it, and we can see that we can make 3 equilateral triangles now, on each side for a total of 6. We see, however, that we can make an even smoother shape by having a greater number of sides polygon, and so a greater number of triangles as a result. For example, we could double the number of sides of the shape, and we remember that half an equilateral or isosceles triangle is a right triangle, so we see that the radius of the hexagon squared equals 1/2 the side length of the hexagon squared plus the radius of the 12-side shape squared. So we apply this with the Pythagorean theorem and solve for the radius of the larger shape in order to approximate the radius of the circle. We can also make a right triangle out of the small space between the hexagon and the larger shape by noticing the radius of the shape that is not encased in the hexagon must logically be the overall radius minus the radius that is encased. However, the other straight end of the right triangle we already know is half the side length of the hexagon, so we plug these in to find the side length of the larger shape. We next find the perimeter of the object by multiplying the length we found by the number of sides, as usual for any regular polygon. We notice the circumference would have to be larger than this amount for the shape or perimeter to be continuous, and if we continue to reiterate this process with bigger and bigger amounts of sides, we will eventually reach the limit of one side of the infinitely sided shape being 2 pi, or approximately 6.28514, so the circumference would reach 2 pi times radius. And since we chose to approximate a circle using an infinite amount of tiny triangles, we can remember the formula for a regular polygon made out of triangles is 1/2 times side length times radius times number of sides. So we plug this in with our circumference of a circle, and since the circumference of the circle equals the number of sides times the length of one individual side, both of these factors are handled by the 2 pi r formula. So we get 1/2 radius times 2 pi times r equals 1/2 times 2 cancels out and you get 1. And r times r is r squared. So our area is proven pi r squared. Join me in the next tutorial video where I discuss a more complicated curve shape, the ellipse. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.